Welcome to the video on parametric equations. Now, what is a parametric equation? It's actually very different than anything you've worked with before. As you can see in this example, we have separate equations for the x and y. So I'm going to write down a little definition here. In a parametric equation, x is written as a function of t. Now, t usually stands for time. It doesn't always have to stand for time, as you're going to see in an example in this video, right? But the reason we use time is because now we can have an equation that actually shows the position somebody or something is at a certain time. That's why we have one function for x and one function for y. So I'm going to say same thing for y. Y is written as a function of t, like I said, where t is usually time. So the advantage using parametric equations is that now, because time has become a variable in the situation, the order in which the points are graphed actually make a difference to how the graph is going to come out. So let's do an example to really start to get a feeling of what's going on here. So we have our x position and our y position defined differently. We're going to come along, we're going to make a table, but we have to plug in t. Now when you're making a graph for a parametric equation, normally, you pick some points to plug in, then you plot those points, and you get this graph. With t being, in this case, time, it does matter where you start and stop. So I'm just going to start at 0 to begin with, and then that's going to get me an x value and a y value. So let's do that. Let's plug in 0 for t. So I'm up here, right? We're plugging in 0 for this t. So we have 3 minus 2 times 0, which is 3. Okay, and now I'm going to plug in 0 for t in the y equation. So we have 1 plus 3 times 0. That's going to get me 1. Now, I could continue plugging in different t's. Now, it is going to make a difference, the interval of my t. So if I go to 1 and then 2 and 3 and 4, I might be missing some little details to the graph by taking, steps of 1. I might need to take steps of 1/2. And we're gonna see that again in another example farther in the video. So I could keep plugging in 1, 2, and 3. I'll do that again. So if I plug in 1 for t in both equations, I get 1, and on this one I get 4. Or I could also notice that x is a linear equation with a slope of -2, which means that these values are just going to keep going down by 2, like so. And y is a linear equation with a slope of 3, so those values are going to increase by 3, if my t is going up by 1, that is. So we have 7 and then 10. Alright, so now let's plot those points. So my first point, and again, this kind of matters because, like I said, it's time. We're kind of tracking the position of something over time. So that says 3, 1. So the starting point is at 3, 1. The next point is at 1, 4. So to go from 3, 1 to 1, 4, I would have to go in this direction. So I'm also going to draw an arrow for the direction that this graph is being made, you could say. Next point is -1, 7. Okay, so then this is the next stop on the journey, and then -3, 10. So notice, when I plot those 4 points, I could keep going, right? If we want time to increase, we know that it's going to keep going in that direction. But I could have started the time earlier, like at -2 or -1. So actually, we know, we know that this is going to get us a line, right? So this is a linear equation made up of linear equations, right, for each position. Now, what if we had said that t had a specific domain? What if we just said you were only allowed to go from 0 to 3? Well, if you could only go from 0 to 3, that would be just this part of the line. And in that case, we wouldn't get a line, we would get a line segment. Okay? So what I like about parametric equations is that you can have a start or a start and a stop, right? Or just a stop to it. You can control certain elements of a function or a graph that you couldn't do when you were in function notation. All right, let's move on to another example. So now let's graph this equation. Now to do this, it might be a good idea to think about t as being an angle, not a time, right? Because we take cosine and sine of angles, not of times. So here's that example where, t doesn't always stand for time. So let's start by making a table. So we have our t, we have our x, we have our y. Right? And it definitely matters where we're going to start this and the step. I'm going to call it the t step that I use to make my table. So let's pick some values of an angle that we can find cosine and sine easily of. So like 0, pi over 2, pi, 3 pi over 2, and 2 pi. So in this case, our t step would be pi over 2, right? Because each time I increased by pi over 2. That is actually going to get us a different graph than if we had graphed a t-step of something like pi, or pi over 4, or pi over 8, right? And you're going to see that because we're now going to try this on our calculators as well. But before we do that, I think we can still just practice making tables first. Let's plug in 0. So cos of 0 is 1, sine of 0 is 0. Cos of pi over 2 is 0, sine of pi over 2 is 1. Cosine of pi is negative 1, sine of pi is 0. And we're on to 3 pi over 2. We're going to get a 0 and a negative 1. And then on 2 pi, we're going to get 1 and 0. So without our calculator, we should be able to know that the graph has a point at 1, 0, right? The position then changes to 0, 1. Notice I'm going to draw my arrows as I draw my points, or else I'm going to forget what came first and what came second. Then we go to negative 1, 0, then 0, negative 1, and back to 1, 0. And now think about that. If we kept going beyond 2 pi, we would just cycle over that picture we already made. So we got a diamond shape. So now let's go to the calculator.
Okay, so on your calculator, the first thing you're going to need to do is change your mode. Normally you're used to changing things from radians to degrees or degrees to radians. Now we're actually going to change from function mode to parametric mode. So we're going to choose par, parametric. And now when you go into y equals, things should look a little different. There we go. We have an x equals and a y equals. So let's enter in our first equation, x equals cosine of t. Notice if you hit what is normally the x button, it will already come out as a t. And then for y equals, we're going to do sine t. Perfect. Let's just check and make sure that we do get this diamond shape. So I'm going to go to my window. And notice it has t-min, t-max, and t-step, right? It's almost like we have these 3 variables that are going to control the window now. So our t-min should be 0. Our t-max should be 2 pi, right? That's the 6.8. And then our t-step, we set it to be pi over 2. So I'm going to actually type in pi divide by 2. We're good to go. So now for the actual part of the window, the x and y axis, we don't need to be from -10 to 10. That's a little big. Let's do -2 to 2 on each of those axes. And let's hit graph. Exactly what we expected it to be. All right, so now the other thing that's important to note that didn't really happen here is that when your calculator graphs it, it actually will graph it in the order that we made the table. Okay, so you'll see the calculator graph that diamond in the order of the arrows that we have written on our note sheet. When we get to some other graphs, I think that will become more obvious. But before we move on to other graphs, I want to play around with this t-step. So if I go back to my window here and I try, let's see, for my t-step, instead of graphing every pi over 2, what if I wanted more points, right? So think of it this way. The more points you put in a table, the more accurate your graph is going to be. So I'm going to do, instead of pi over 2, let's do pi over 4. So every pi over 4, it's going to graph a position. So notice what we're stopping kind of in between those axes, right? So it's pretty octagonal. If I go to, let's go to pi over 8 as our t-step, we would expect even more of those. And it looks like we are getting closer to a circle. So let's put in a really, really small number here. Let's do pi over, let's do over 100. And you can see that we do get a circle. Now it looks like an ellipse, but remember that our screen is kind of stretched in the x direction. But yeah, does it make sense that we're getting a circle? Something to think about. We have a cos and a cosine of a t and a sine of a t. Think about that in class. All right, now before I move on, I just wanted to do one other thing, whoops, and that is to do a smaller, instead of a smaller t-step, a larger t-step. So we were doing pi over 2. What if we did pi? Interesting. We don't see a graph. But that should make sense because the only points that would show up are 1, 0 and -1, 0. So it's really just a graph kind of riding that x-axis, right? So it's not that the calculator is broken, it's doing exactly what we're telling it to do.
So the next type of question that we're going to think about is actually going from parametric form of an equation to what we're going to call function form, the form that we're used to dealing with. So we have an x equals 6t, a y equals 3t squared. How are we going to eliminate the parameter, meaning eliminate t? Well, we need t to disappear, and it looks like we have two equations. We're basically going to set up a little substitution. So I'm going to take my x equals equation, and I'm going to solve that for t. So t would equal x over 6. I'm now going to substitute that into the second equation. So we get y equals 3 times x over 6 squared. Let's just simplify that. 3x squared over 36. So y is going to equal x squared over 12. You might like that better as 1/12 x squared. So what we did, we substitute into t. We now only have x's and y's. We've eliminated the parameter, and notice what we have. We have a parabola. Would you have guessed that we have a parabola from the original parametric equation? Perhaps. Notice that the y position is defined by a quadratic function, where the x is defined by a linear. Okay, so not both of them, not both of them were quadratic, just one of them. Again, something to think about for later. How about in this example? How would we eliminate the parameter here? Oh, well, it's the same idea, right? We have an x equals and a y equals, and it's in terms of t, so we're going to do some substitution. But think about how you would get t by itself. Wouldn't you have to take the cos inverse or the sine inverse? Something feels weird about that. Let me give you an idea of what you should be thinking. So on the other problem, we really could have kind of guessed that we're going to have a parabola. Could we guess what type of equation this is going to turn into? We have a cosine and a sine, and notice the coefficients are different. Well, think about equations that have cosines and sines in them. But think about what you do know about an equation with sine and cosine in it. Don't we have a trig identity for sine squared of x plus cos squared of x equals 1? And isn't the unit circle made up of points, where the points are defined as cos theta, sine theta? So I'm feeling that this has to be something like a circle, but I'm getting more of a feeling that it's probably an ellipse, because these coefficients are different. All right, now if you want to kind of confirm that, you could type it in your calculator. We could see that it's an ellipse, or you could make a table yourself and graph it. You'd see that it's an ellipse. So having an idea in mind of what this equation should look like in the end is a really, really helpful method. So I'm just going to jot it down at the end here. The equation of an ellipse looks something like this. X squared over some value squared plus y squared over a different value squared equals 1. So we're going to get our x equals and y equals equations to look something like this. So how do we get there? Well, the first thing I would notice is we don't have x's and y's. We actually have x squareds and y squareds. So let's square both sides of these equations. Okay, so if I square both sides, we get x squared equals 4 cos squared t. Over here, I would get y squared equals 9 sine squared t. Okay, so we have our x squared and y squared, but we have to get them together, right? So we're going to have to add them together. You know what? This is where I'm kind of going to give you a little hint here. If I add them together now, don't write this down, but I want you to see what's going to happen. If I add them together now, x squared plus y squared would equal 4 cos squared t plus 9 squared sine squared t. And I don't like the 4 cos squared and the 9 sine squared. The 4 and the 9 are throwing me off. I wish that they weren't there, because I know something about cosine squared t plus sine squared t. That's 1. Oh, and that would be awesome, because shouldn't my equation have a 1 in it? So can we somehow either get rid of or move these 4 and 9 coefficients before we add these together? Well, yeah. Don't we know where we want them to wind up? Aren't these constants on the bottom? Yeah, we want to move this. So let's divide this side and this side by 4, right? So we get x squared over 4 equals cosine squared t. Let's divide each of these sides by the 9. So I get y squared over 9 equals sine squared t. This is much better. It's already looking like that. X squared over 4. Now I'm going to add it with the y squared over 9. That's going to equal cosine squared t plus sine squared t. Awesome, because we know that's 1. And there you have it. It's exactly what we thought it would look like. We have an ellipse whose center is at 0, 0, and is more tall than it is wide, right? Because of that 9 underneath the y squared. That's talking about the vertical axis of the ellipse. All right, so I've given you some really good examples to kind of springboard off of when you're working on the classwork. Like I said, you haven't So just like always, you haven't seen every single example in these videos, but they're a really good taste of what you should be doing when doing those new types of problems. So good luck.